Alright, so just let me start now. So once again, I'm going to finish the chapter 11 today. And then we can set some time for the review session this week. Next week is the exam week. So I think we better have some, at least one or two review sessions so we can prepare for the exam too. So last time we talked about the SN2. If you guys watched the video like on the last Friday, we kind of stopped where we had a solvent. The solvation is kind of a big role in just the SN1, SN2, E1, E2, sort of all the mechanism in chapter 11. So the last part of the chapter, the SN2 part is about that they need to use polar 840 solvent. So actually SN1, SN2, we both use the polar solvent, but the aprotic means the one that doesn't make a very strong like a dipole protection like a hydrogen bond. So whenever you do certain type of reactions like this one, you can actually have some different reactivity with the different types of the solvent. So for example, obviously we wanted to have the aprotic solvents like this one. So those are the ones that makes sort of a hydrogen bond, maybe not so good solvent here, but we can have some other compounds like DMSO, dimethyl sulfoxide, dimethyl formamide, and also we have some the other compounds like this one. Here actually, yeah. Oh, sorry. So as you can see, this is the kind of order of the solvent. It shows the different reactivity for SN2. So the one on here on the left side will be the kind of the less reactive. This is the one in more reactive over here. It's just simply because of the, it's better we use polar aprotic solvent. That's why it shows different reactivity here, which I also kind of wanted to remember, because when we go into SN1, you will see a lot of opposite vectors, not even just for the solvent and a lot of things. So once again, if you can have some time, to watch the lecture on last Friday. It was mainly for SN2. Okay, so if that was the SN2, what about the SN1? So this is something you can do with some compounds with very highly substitute with the argues or the arcing. So whenever you have this type of compounds, or you can say switch to any living groups, which is quite okay. But the problem is you have a 3 argues over here. It's very highly substituted. So based on what you learned from SN2, it might be very not so good compound to do any substitution reaction like this one. But the thing is, if you try to use nucleophile, which is not so strong, like the water can be also kind of behave as a base, so it can work as a nucleophile but not so strong. Okay, so if that is happening, what you can find out in the experiment is actually this one. So this one, it actually happens quite fast. So this is a kind of something that we didn't expect when we studied for the SN2, because this is really bulky compounds that you can do really the nucleophilic attack from the back. Do you guys you guys watch the SN2? The last Friday. So this is why the scientists kind of wonder why. Why is it happening? Because it should be very slow reactions. And also it's kind of not so strong nucleophilic attack here, but it actually happened quite in a fast pace. So there gotta be a reason why that explains why it's happening in a quite a fast pace, even though it's a highly substitute, not so strong nucleophilic attack over here with the water. It's not even a negative charge here. It's quite neutral. So this is the one we call SN1. So you will see a lot of things different from SN2. It's quite opposite the other way. So once again, it's pretty much the same for the nomenclature though, for the, except the last one. This is the substitution. So you're substituting by nucleophile, right? But it says 1 because the SN2 is bimolecular, but this is actually unimolecular. So that means, kinetically speaking, SN2 was about the weight was equal to K, and your compound, and also your nucleophile. Both of the concentration really matters to the speed of your reactions and for SN2. But this is unimolecular, meaning there is only one that matters for the reactions. This is the rate constant, so you don't have to really worry about this one, but this one. The concentration of your compound is the only thing that matters for deciding how fast your reaction will be happening. This is what we call this SN1 and unimolecular, so we call this SN1, not 2, but we learned last time. So we got to here why this is the only thing that really matters to the rate of the reaction, how to determine how fast the reaction will be. Because of this one will have 2 steps. So the SN1 had only 1 step. So the attacking, the nucleophile attack, and also the breakage of your leaving group bond will be happening at almost simultaneously. But in here, it happens in 2 different steps. The first step is where you're going to get carbocation. So this is where you're going to have, so if you have a highly substitute, like a leaving groups over here, they're actually going to break apart first. This is the first step. Then they will leave carbocation over here. I'll give you just, so for here, if that was the case, this will lay over here, right? So they become carbocation. This is the first step, okay? So this is the first step. And now the second step is that now you have water and attack here. You're looking for something that's positive, so this is looking for the attack here. So this is the second step. The thing was, when scientists tried to measure the speed of these 2-step reactions, this reaction was very slow. The first step was very slow. So making this compound to lose the leaving groups, so they can become the carbocation form, was quite slow step. But this was really fast, almost like 1,000,000 times faster than the first one. So that only thing that really determines how fast your reaction will be in SN1 is only the first step. This is why the concentration of this one is the only thing that matters to the rate of your SN1 reaction, the substitution reactions. Kind of makes sense, right? Okay. So, so this is the thing, and also this one actually explains why. This also explains why, even though this is a highly substitute, that makes the good nucleophilic attack to this one in SN1, because If it's happening not at the same time, so those two, so the nucleophilic path, like here to, okay? If it is happening not at the same time but separately, this one is slow. So to have a more stable cation is more important for direction to go forward, rather than having those two at the same time. Because they're doing now separately, not at the same time. So your nucleophile is not that strong. So they can do those two jobs at the same time. It's impossible. So the first thing they really need to do is making one step first, and so become a carbocation form. So better, the stable carbocation will make much faster reactions in SN1. So this is completely the other way in SN2. Whenever it's more substitute in a compound, strong nucleophile cannot come into the bulky groups here in the back, because they're always coming from the back side of the where you can find the leaving groups. But this one doesn't have to, because they don't have to do it at the same time. So when they leave leaving groups, they leave and then they come in. So they don't have any space problem over here. But the most important thing than the spacing problem for SN1 is they need to have a stable carbocation. That's the better, it is more important thing they need to have for SN1. Make sense, right? So that is why, if that is the case, here's the thing. So this is totally opposite from carbocation stability. If you guys remember, if it's more substitute with the R groups, it's much more stable. So this is methyl. There's no R groups here, right? This is a primary. And then you have a, let me actually just delete some amount of space. So this is a methyl again. This is a primary, because you have only one R group over here, right? And the secondary, well, I'm going to show you a bit more. I hope you guys remember this one. This is what we call alytic position of the cation. So they can have a resonance structure is more stable. And this is also the same reason. This is a benzylic position of the carbocation. And this has also similar to the secondary carbocation. So maybe you can say R hydrogen cation. Those all three has a similar stability in here. And obviously, the tertiary, like this one, is the best one, because that gives the most stable form of the carbocation that makes much easier SN1 reaction when you have a nucleophile coming in contact here. So this is totally opposite from what we did for the SN2. So SN2 is more bulkier in your compound. That will be much harder for the reaction to go forward. But SN1, if it's the bulkier, it's more substitute on that where you can have a carbocation form. That will actually make easier and faster reaction. Make sense, right? So this is something and that we can find out from comparing SN2 and SN1. So this is more substitute. It's better for the SN1 actually. But for SN1, you don't have to have a strong nucleophile. Actually, it's worse if you have a strong nucleophile. So the water is actually kind of one of the best candidates for SN1. So the leaving group wise is almost same that we saw from the SN2. So this is this is the So this is almost same you saw before for the SN2. So hydrox group will not be, it's very poor leaving groups. So if this has a leaving groups, reaction will not be so fast. But here, if you have a much larger and larger, the halogen groups over here have a better ability to arrange the electron charge. And also this is as good as the almost cross-layered groups. And also the water is really good leaving group as well over here. So whenever you have a, maybe for example, this one, this is perfect for the SN1 because it's highly substituted here in this compound where you can possibly have a carbon cation. But the problem is you have the hydrox group as leaving groups. This will not leave so easily because this bond is quite strong here. So in that case, what you can do alternatively is you can do HX. So let me explain why. So if you do like a HX form, like a hydrobromic acid here, what happened to this one is they switch hydrox group to water. They're grabbing this one to here. And then now you have a water as a leaving group, which is what? It's a really good one. So in this case, whenever you have some poor leaving group like a hydrox group, you can treat it with the HX, and you can have you can switch it to the water groups, which is really good leaving groups. Then this comes in when so it left first, and then later it comes to that carbocation position, so they can be substituted. Over here. Kind of makes sense, right? Can I move on? Makes sense. All right, so it all makes sense. I think I have some questions for you. Can try. Oh yes. So if you have this one, maybe I can put this the one. Oh. You can also kind of treat this one with the acetate ion. Actually, this is coming from sodium acetate. Will be dissolved in acidic solutions. And they're actually in a water base. There's actually, I forgot to tell you, but there's one more thing that I need to tell you is SN1 reactions. You need to have a polar solvent too. But it's much better, a lot better, if it's the like water or like a methanol or ethanol that has a ability to make some hydrogen bond. Here's the reason why. So whenever you look at the reaction, any substitution reaction like this one, if you just look at the solvent right here is in water, you can always expect that it's SN1 automatically. Because the water would be, once again, poor solvent for the SN2 because of the, actually I told, you can check the video on the Friday, that makes the high energy in the reactants, so that makes a lower activation energy. That is why it's good for SN2. But here, once again, unlike SN2, SN1, more stable carbocation is more important job than having this high energy steric reactants. So the water can make carbocation much more stable. So that makes your energy diagram, it doesn't have to be started from here, but they can actually lower. Let me drop it here, I'm sorry. So SN2, that makes the if reaction goes up here, this is the activation energy, this is the amount of energy. If you have a big activation energy, means this is slower, because that means you need to have a lot of energy to make reaction go forward. But the SN2 is non-aprotic that makes much higher position it can start, because it will be barely solvated by the solvent. So this will actually lower. So this is why it's better for the SN2. But here, once again, this will happen in 2 steps. So like this way. And in this way, you don't have to lower this one. Actually, you can make this transition and the intermediate state lower. So you actually make it this way. Because this will make your much more stable carbocation transition to the carbocation intermediate. So that makes, so you loading from the top, unlike you did loading from the bottom. Because it happens in a different mechanism. It's a 2-step. The most important thing in here is always carbocation. So that is why whenever you see the reactions in the exam that is in the water, it's just SN1 for sure, 100%. Makes sense, right? So only thing you really, I'm sorry, you don't have to know what I just told you here. Only thing you really have to know is that if that is in a water-based solution, you can just say, oh, this is SN1 for sure. So I can do SN1. And also it kind of makes sense because this is the secondary position over here, and also plus, this is the benzene, it's the benzylic position as over here too. So this is also good for what? SN1. This could have been harder for the SN2 reaction because this is quite bulky here, this position. It will be quite bulky. So this will be for sure SN1 because of the solvent, and then we can find the position of the carbon, we can substitute the halogen. It's quite bulky there. And also, if you look at the ester anion, this is also quite bulky too. I mean, not really bulky, but it's not as bulky. It's really much more bulkier than just hydroxide anion. So this also we're having a hard time coming from the back here because it's also bulky, and liquid by itself is kind of bulky too. It gotta be SN. So this one remains. Oops. This one. So this will be substituting this one. So we have this. Okay. Makes sense, right? So if you see some bulky compounds with the halogen groups, and you don't see very strong, like some are okay, but not so strong base or the nucleophile, or usually neutron form, usually it doesn't really matter. And also, most likely the solvent is water-based. Oh, this is SN1 for sure. If it's not, it's a less, it's a primary alkyl, and you have a very strong, like a nucleophile, that gotta be SN2. So, if that is the case, can I move on, right? If that is the case, here's the thing. SN2, this one. SN2 shows the inversion of your RS configurations. Because like I said on the last Friday, the nucleophile are always coming from the back side, opposite side of where you can find the halogen. But SN1, they don't have to, because once again, if this is the leaving groups over here, nucleophile comes in, and they're actually going to have it happening at the same time for SN2, right? So this is why they're always coming from the back, because this is already there. So they can come into the way that the leaving group is, because there's already leaving group taking up space. That's why it's better for them to go in from the back side. This is why whenever you have a SN2 reaction, the configuration will go the other way. Kind of makes sense, right? Because the way you can find the halogen will push to the other side and leaving, and then coming to the edit on the compound, but on the opposite side. That is why your RS configuration will be inverse. There will be opposite side. But SN1, there's no space problem once again. you have a carbocation, right, in the same plane right here, but there is some empty because the leaving groups already left, so now it's carbocation form. But this nucleophile now can call, they don't have no space problem here, right? It's already left. So you can come in this side, no problem. So that means if this is the position, or if this is the position where you had a halogen groups initially in the reactance group, you're going to show inversion or retention of the compound will happen half and half. So, because the chance for this nucleophile taking this side or this side is 50-50. But if this side is the way you had a leaving groups, or this side doesn't matter, because it will have an equal chance. 50. Equal chance for the nucleophile attacking on these two sides of the compound, because you don't have a leaving group anymore. It's the first step is already done. So, if you have a for SN1, if you have like an R configuration form in this specific point in the chiral center, it could go the S, or you can also could go R 50%, 50%. That's a theoretically yield numbers. But realistically, so once again, do you guys remember the step 1 is slow, step 2 is really fast, right? So this is what we call this SM1. So step 1 is what we call rate limiting steps or rate determining step. Means this is the only step that actually going to determine how fast reaction will be. So meaning when the leaving groups either leaving from here or here doesn't matter. If they leaves the compounds there, and as soon as it leaves, this one will attack right after, right? That's why the step 2 is really fast. Meaning, as soon as it leaves, it's just coming right after it. It's so quick, it's so fast. The meaning, realistically speaking, this is the chance you should see, but the where you could detect the inversion of the reaction is a bit higher, slightly higher. Like you can say 60 to 40, 70 to 30, but it doesn't really go above like a 80 or 90 now. But slightly speaking, still inversion is a bit more preferred because like I said, let's say we had a hydrogen right here. So it has to happen right away, meaning they got here. So carbon cation is here. So if it bound to the this side, right, once it's left to the compounds, there's slightly bit of a there's still kind of weak the ion interaction over there. Because the leaving usually takes the pair of electrons there to make this obviously carbon cation is positive charge, but it has to happen almost the same time. So there's slight bit of like interfere on this side still. So it actually slightly better if they're coming on this side anyway. Even though there will be some space available, this guy still might hang up instant time a bit more. So in real time, this might be slightly more favoring inversion anyway still, but it has to be racemic mixture. It's not always going to be inversion like you saw in SN2 because of this. Makes sense, right? Okay. Can I move on? So as you can see, there's a lot of things that's different from SN1 and SN2. But this is pretty much it. I want to, oh, it's actually pretty good. So once again, I'm gonna put more questions from SN1 and SN2 rather than E1 and E2, which is for elimination. But I'll still do elimination just for a bit more. But you'll see more questions coming from SN1 and SN2. I'll tell you what type of question you may see on a few from elimination. So whenever we have an elimination here, This one also has E2 and E1. But I covered the textbook covers the SN2, SN1 first because it's really similar to, this is really similar to SN2. This is really similar to SN1. I'll tell you why. So obviously, this one will also have a, this one will also have a carbocation intermediate. This will not. So this elimination also happening at the same time as it does in the SN2. And here, this will be eliminated by 2 steps as well, too, like it did in the SN1. So they're pretty much similar. So we kind of named it in this way: E1, SN2, then E2 and SN2, and E1, SN1. They're both similar to each other. But just instead of substituting your leaving groups, they're actually going to remove all. So whenever you have the groups, this one minus, sorry, going to have elimination. So you don't have to know. Sometimes there's conditions where the nucleophilic attack just the substitute your leaving groups. But sometimes it eliminates your leaving groups, but just putting the double bond, so you can have alkene compounds after elimination reactions. Because there are temperature issue too, and there's also if you have a very strong nucleophile coming into the compound that is really bulky, but the solvent is not water, those type of things, they can do the substitution, but only elimination. But you don't have to know. But there's one really important rule I want you to know for elimination. This we're going to examine is the Dice rule. This is one I want you to kind of so for the example. So whenever you have some kind of like compounds with the halogen group or leaving group, you can say you can treat it with ethoxide with some ethanol or some air. But if you try to do this one here, they're actually going to not substitute, but just going to eliminate it. But like I said, the elimination process will remove either grabbing the hydrogen, so that goes to this one, and then leaves over here. But the problem is you can have other options too over here, because there's also hydrogen too. So they can take this one, they can go this one, and this one this way. So you have two possible scenarios. Because you have the leaving groups where you have a neighboring carbon also has a hydrogen, so it can be eliminated together, so they can make some alkene groups over here. So in the two scenario, you can either have this one or this one, because this is number 2, this is number 1. So this is one thing I want you to remember for the exam is this will be major product. I think it's about, so it's 81%, and this is about 19%. I'm not sure if I'm right, but anyway, the more substitute alkene is will be the major product. Will be more favored in this elimination reactions here, and this is what we call Zaitsev. So whenever you have elimination reactions, there are 2 possibilities you can go through, but you can have either this scenario and this scenario. Then you can try to draw the way you can put the double bond in this compound. This is number 1, because this is coming on this side, and this coming on this side. So it'll be number 1 and 2. But if you look at this one here, this is a mono substitute, because there's 3 hydrogen over here. If you don't see it, it's implied there. But as you know, it's double bond. So there will be 1, 2, 3, 4, 1, 2, 3, 4. You know this by now, I'm pretty sure. But so this is a mono substitute, but here is di substitute. So it's the same. The tri substitute is better than di substitute. Di substitute is better than mono substitute. And which one is whatever the one is the more substitute will be the major product, the other will be the minor. Kind of makes sense. Let me give you one more example. We're almost done, I promise you. We have this one over here, okay? We have this one over here. And then we can treat it with the potassium hydroxide and ethanol. So here's the thing. As you can see, this one has to be either SN2, the SN1 or E1. But this is a very strong nucleophile because you're going to have a hydroxide anion. But this is the kind of really bulky groups over here. You cannot do SN2 either. So they will do for sure not substitution but elimination. So the possible scenario here is you can have either you can also have the ones over here. You have the ones over here. So either you can have this one to grab in here, or you can either grab this one to be here, right? So you can have this one, either way, because this will be the same anyway. You see this one, right? Either you have a double one here or here will be the either this one anyway, because you just So anyway, so can you guys guess now which one will be major, which one will be minor? So this, if you look at the double bond over here, this is di substitute. This is the 1, 2, 3. So this is tri substitute. Which one do you think would be major? Right. Perfect. That's all you need to know. Because there will be elimination reactions. Yeah. So then, whenever you see the two possibility here, you can try to go with this one. So in the exam, maybe I'll show you this, and just try to pick which one is major, which one is minor. You can go with the one with more substitute. Very very easy question you can answer by just looking at the picture, the diagram. You can actually answer it. It's not that hard, right? It's just you just need to know what rule really means, what the Dicey rule means, and everything. Almost steps. All right, so we're down to the last one. This is so E1 is once again you're going to have carbocation, right? I said carbocation. So whenever we have an elimination, E1 elimination process over here, this will also happen in 2 steps, meaning you're going to have a carbocation first, meaning you're going to have this one, leaving groups will leave first. So this will leave first, so will become carbocation, or it could be anything. And then your nucleophile, like just a nucleophile, it comes and get it. So it becomes eliminated. So it's 2 steps. 1 step and 2 step. You have this one over here. This is very similar to SN1, right? But instead of replacing the hydrogen, also the position is different. But instead of substituting, they're eliminating those 2. Okay. So E2, you can actually estimate like this one right here. If you have So this is happening in an anti-pair planar position. You don't have to know this one anyway. But in this way, so in this way, this is E2 like SN2. It's happening at the same time, almost the same time, simultaneously. So this is what we call this E2. So E1 is the same as the SN1. They will have an intermediate, carbocation intermediate happening in the two steps. And then E2 is like the SN2. It happened all the same time because this is quite strong. So they have a very sequential but very simultaneous reaction at the same time. They're winding and grabbing this one and breaking these two bonds almost happening at the same time as E2. Makes sense, right? It's very similar to the SN2 and SN and E1. There's one more thing. They additionally mentioned in the textbook is the E1 CB. So this is actually kind of weird because they break this one first. So they become not carbocation, but they're going to become carbanion. Carbanion. So this is the carbon with the negative charge. Unlike the one with the positive charge, we call carbocation, which is carbanion. This carbanion is the carbon with the negative charge, and then they move this one to the double bond, and then the leaving group leaves after. So as you can see, this is not so it's not common. As you can see, right? The carbon related to have a positive charge, but the negative charge carbanion is kind of very unusual. So this is only happening when it has very, very poor leaving groups. So to have this one to leave, they should have this kind of unique mechanism to make it leave. Because this is not so good leaving groups. Sometimes compound can do this one, the E1CB. They usually do it with the the carbonyl groups over here. So if you have over here, they can break the bonds here. So they can go to actually here. So this is where you have a very poor leaving group over here, but they can just take it off because it's very strongly bound to this one. So, but if you have a carbonyl group with oxygen, they can do very sequential. So if it goes here, they can go here, so it can be lone pair, but it goes down again, and this goes to this one and goes to this one. So this one is you don't have to know this one for sure, but this will make, do you guys remember this one? This is, you see this is the double bond lone pair kind of going off from the other carbons in a row that makes really good resonance structure, right, among those three, without oxygen over here. So this will make quite strong force to make this poor leaving group to leave. This is what we call E1CB, but you don't have to know for this. This is just for your, I'm pretty sure you have a much more chance in more detail. Are you guys taking over too? Yeah, so this will be covering chapter 22 and 27. So you get the more mechanism too. So, but you don't have to know for the exam too. Thank you guys, that's it for today. So I'll try to,